All right, let's talk about solutions. We're going to dive into the surprising science of mixing. The invisible forces that decide why some things dissolve and others just don't. And we'll see how that simple act creates some pretty amazing effects we see all around us. So let's start with a classic wintertime puzzle. You've definitely seen the big trucks out there spreading salt all over icy roads. But have you ever stopped to wonder, why salt? Why not sugar? It looks kind of similar, and it dissolves in water, right? Well, the answer is hiding in the secret world of molecules. So let's zoom in and see what's really going on.
To really get what's happening with mixing, you have to think small, like really, really small. See, at the molecular level, it all comes down to attraction. You can think of them like secret handshakes between molecules. Some are super weak and quick, others are really strong and they last. These little attractions, they're called intermolecular forces. And trust me, they're the key to this whole story.
So let's start with the most basic handshake of them all, the dispersion force. Just picture this. In any molecule, you've got electrons just whizzing around. For a split second, you might get more of them on one side than the other, and that creates this tiny, temporary charge. Well, that fleeting little charge can attract a neighbor, making a very weak bond. It's temporary, sure, but here's the thing. Every single molecule does this.
Okay, but what if that attraction wasn't just a fleeting thing? Well, some molecules, what we call polar molecules, have permanent positive and negative ends. They basically act like tiny little magnets. So naturally, the positive end of one molecule is attracted to the negative end of its neighbor. This is a dipole-dipole force, and it's a much stronger, more stable connection.
And then you have the superstar of the dipole-dipole world, the hydrogen bond. This is a special, extra strong version that happens when hydrogen is bonded to a really electron-greedy atom, like oxygen. This creates an incredibly powerful attraction. Water is the textbook example here, and its hydrogen bonds are exactly what makes water so unique. Okay, so let's just quickly put this all together. At the bottom, we have those weak, universal dispersion forces. A step up from that, you've got the stronger dipole-dipole forces for polar molecules. Stronger still are those powerful hydrogen bonds. And then right at the top of the list, you have ion-dipole forces. That's the attraction between a fully charged particle, an ion, and a polar molecule. This ranking, this hierarchy of strength, that's what matters. All right, so we've got this whole menu of forces, these different molecular handshakes. How does that help us figure out what's actually going to mix together? Well, it all boils down to one simple, absolutely golden rule. Like dissolves like. So when we say something dissolves, what's actually happening on an energy level? Let's break it down. Think of the liquid as the solvent and the stuff we're dissolving as the solute. First, you have to spend some energy to pull the solvent molecules apart. Second, you spend more energy to break the solute apart. But then, the payoff. When they mix together, new attractions form, and that releases energy. If you get more energy back than you put in, they're going to mix, no problem. And this is exactly why that like dissolves like rule works. Polar solvents, like water, have really strong attractions to each other. So they only get a big energy payoff when they dissolve other polar things. But when you try to mix in something nonpolar like oil, there's just not enough energy released in the mix to make breaking those strong water bonds worthwhile. It's kind of like trying to mix magnets and marbles. The attraction just isn't there. Okay, so now we get why things mix. But the really cool part is what happens after they mix. See, the simple act of dissolving something in a liquid can fundamentally change the physical properties of that liquid in some pretty dramatic ways. This leads us to this really important idea called colligative properties. And I promise, it's simpler than it sounds. These are properties that change based only on the number of particles you dissolve, not on what those particles are. The identity of the particle, its name, its type, none of that matters. It's all about the quantity. More particles equals a bigger effect.
So let's look at the two big ones you see all the time. When you dissolve something in water, those new solute particles basically get in the way. They make it a lot harder for the water molecules to line up and form a nice, neat ice crystal. That means you have to get things even colder to make it freeze. We call that freezing point depression. And the same thing happens with boiling. The particles make it harder for water to escape as a gas, so you have to crank up the heat even more to get it to boil. That's boiling point elevation.
And just like that, we are right back where we started. Both salt and sugar will lower the freezing point of water. So if the effect only depends on the number of particles, what makes salt so much better at melting ice? Well, the answer comes down to one last little detail. It's called the Van Hoff factor. All this is, really, is a number that tells you
how many separate particles a substance breaks into when it dissolves. For something like sugar, which dissolves but doesn't break apart, that number is just 1.
But when you look at something like table salt, sodium chloride, it's a whole different story. The Van Hoff factor is not 1. As you can see right here, it's 2. And this simple difference, well, it changes everything.
And this is the big reveal. When a sugar molecule dissolves, it just kind of floats around as one single particle. But salt is an ionic compound. When it hits water, it splits apart into 2 separate ions, a positive sodium ion and a negative chloride ion. So for every single unit of salt you add, you actually get 2 particles in the water getting in the way. Twice the particles means twice the ice melting power. And that is why we use salt to clear our roads.
So let's go from those tiny molecules all the way back up to our world and put this all together.
So let's just zoom out for a second and look at the journey we took. It all starts with those invisible handshakes between molecules, right? The intermolecular forces. Those forces give us the golden rule: like dissolves like. And that simple act of mixing is what creates these powerful, real-world effects, the colligative properties that we see and use every single day.
And that kind of leaves us with one last big question to chew on. We've seen how dissolving a solid can completely change water, but what about gases? The same rules apply. So how did dissolved gases like oxygen and carbon dioxide go on to shape our entire planet's oceans and the very air that we breathe? Well, that's a story for another time. Thanks for joining this explainer.